Every day, massive power plants convert enormous amounts of fuel into electricity that keeps cities, factories, hospitals, transportation systems, and millions of homes operating. From a distance, a power station may look like a collection of chimneys, cooling towers, pipes, and industrial buildings, but inside, thousands of machines are working together in a carefully controlled sequence. The basic idea is surprisingly simple. A fuel source is used to produce heat. The heat creates high-pressure steam or hot gases, and that energy is converted into mechanical motion. A turbine then spins a generator, and the generator produces electricity that can eventually travel hundreds of kilometers through the power grid. But turning fuel into reliable electricity at this enormous scale requires sophisticated engineering, precise control systems, and multiple layers of safety. The process begins with the fuel. Depending on the type of power plant, that fuel could be natural gas, coal, oil, biomass, or another combustible material. Natural gas is widely used in large power stations because it can be burned efficiently and can respond relatively quickly to changes in electricity demand. Coal-fired plants use solid coal that must be transported, crushed, and prepared before combustion. Oil-fired plants can use liquid petroleum products, while biomass plants may burn materials such as wood pellets or agricultural waste. Although these fuels are very different, their role is similar. They provide a concentrated source of thermal energy that can be transformed into electricity. At a conventional steam power plant, the prepared fuel enters a massive boiler or furnace. Here, controlled combustion releases chemical energy as intense heat. In a coal-fired plant, powdered coal mixes with carefully measured amounts of air and burns inside a huge furnace. Temperatures can become extremely high, producing enough heat to convert large quantities of water into high-pressure steam. The walls of the boiler are lined with thousands of tubes containing water. As the furnace releases heat, energy passes through the metal tube walls and heats the water inside them. The water used in a modern power plant is not simply ordinary tap water. It is treated extensively to remove minerals, dissolved gases, and impurities that could cause corrosion or deposits inside the boiler and turbine system. Water chemistry is extremely important because the equipment operates under high temperature and pressure for long periods. Even a small buildup of unwanted material can reduce efficiency or damage expensive components. For this reason, power plants continuously monitor the chemical condition of their water and steam using specialized instruments and laboratory equipment. As water absorbs heat inside the boiler, it changes into steam, but the steam leaving the boiler is far more energetic than the steam produced by a household kettle. It is created at extremely high pressure and temperature and is directed through large, heavily insulated pipes toward the turbine building. In many steam power plants, additional heating systems raise the temperature of the steam after its first expansion. This reheating process improves efficiency and reduces moisture inside the later stages of the turbine, protecting the turbine blades from excessive wear. The turbine is where thermal energy begins its transformation into mechanical energy. A massive turbine contains multiple rows of carefully shaped blades mounted along a rotating shaft. As high-pressure steam rushes through the turbine, it expands and loses pressure. During this expansion, the steam pushes against the turbine blades, causing the shaft to rotate at high speed. Different sections of the turbine are designed for different pressure ranges. The high-pressure section receives the hottest, most compressed steam, while the intermediate and low-pressure sections continue extracting useful energy as the steam expands. The turbine shaft is connected directly to an electrical generator. This is the point where mechanical motion becomes electricity. Inside the generator, a rotating magnetic field moves relative to coils of conductive material. That changing magnetic field induces an electric current in the coils. This principle, known as electromagnetic induction, is the fundamental process behind most large-scale electricity generation around the world. The generator can produce enormous amounts of electrical power while rotating continuously at a carefully controlled speed. In many large steam plants, the turbine and generator rotate at either 3,000 or 3,600 revolutions per minute, depending on the electrical grid frequency and generator design. Maintaining the correct rotational speed is critical because the generator must remain synchronized with the grid. If the speed or frequency changes significantly, the plant can become unstable or disconnect from the electrical network. Sophisticated control systems constantly adjust fuel input, steam flow, and other operating conditions to keep the generator synchronized while responding to changes in demand. After passing through the turbine, the steam has released most of its useful energy. Instead of being thrown away, it enters a large condenser where it is converted back into liquid water. The condenser contains thousands of tubes carrying cooling water. When the exhausted steam comes into contact with the cold surfaces of these tubes, it loses heat and condenses. This creates a low-pressure environment at the turbine outlet, allowing the steam to expand more efficiently and extract additional energy from the turbine. The heat removed from the condenser must go somewhere. In some plants, cooling water is drawn from a nearby river, lake, or ocean and returned after its temperature has been carefully controlled. Other plants use large cooling towers. Inside these towers, warm water is distributed over specially designed surfaces while air moves upward through the structure. A small portion of the water evaporates, carrying heat into the atmosphere. The large white clouds seen above many cooling towers are mainly water vapor and tiny water droplets, not smoke from the fuel combustion process. Once the steam has been condensed back into water, powerful feedwater pumps send it through a series of heaters and back toward the boiler. The cycle then begins again. This continuous loop allows the plant to reuse most of its working water rather than constantly replacing it. Every part of the cycle is monitored because even small losses of pressure, temperature, or water can reduce the plant's efficiency. Engineers therefore track thousands of measurements to ensure that heat and pressure are being used as effectively as possible. Natural gas power plants can use a different system known as a combined cycle gas turbine. Instead of first producing steam in a traditional boiler, natural gas is mixed with compressed air and burned inside a combustion chamber. The extremely hot expanding gases rush through a gas turbine, directly spinning the turbine blades. This first turbine is connected to a generator and produces electricity, but the exhaust gases leaving the gas turbine are still extremely hot, so the plant does not simply release all of that energy into the atmosphere. Instead, the hot exhaust passes through a heat recovery steam generator, often called an HERSG. This system captures the remaining heat and uses it to produce steam. The steam then drives a second turbine connected to another generator. By extracting energy from the same fuel twice, first through the gas turbine and then through the steam cycle, a combined cycle plant can achieve much higher efficiency than a simple combustion system. This is one reason natural gas combined cycle plants have become an important source of electricity in many countries. Regardless of the technology used, controlling the plant is a massive engineering challenge. A large power station contains thousands of sensors measuring temperatures, pressures, fuel flow, steam flow, vibration, electrical output, water chemistry, and equipment condition. All of this information is sent to a central control room where operators can see the condition of the entire plant in real time. Large digital displays show whether each system is operating normally, while automated alarms immediately warn operators if a measurement moves outside its safe range. Automation allows the plant to respond much faster than human operators could manage manually. If electricity demand suddenly increases, the control system can increase fuel flow and adjust steam or gas turbine output. If a critical temperature becomes too high, protective systems can automatically reduce power or shut down specific equipment. Computerized systems also coordinate pumps, valves, fans, burners, compressors, and cooling equipment so that the entire facility operates as one integrated machine. Safety is built into every stage of the process. Combustion equipment is equipped with flame monitoring and automatic fuel shutoff systems. High-pressure steam systems contain pressure relief devices and emergency isolation valves. Electrical equipment includes protective relays and circuit breakers that can disconnect damaged sections within fractions of a second. Fire detection and suppression systems protect buildings and critical machinery, while backup power supplies keep essential control and safety systems operating if the main electrical connection fails. Environmental control is another major part of modern power generation. Plants that burn coal or oil must deal with gases and particles produced during combustion. Advanced filtration and emissions control systems can remove much of the particulate matter, sulfur compounds, and nitrogen oxides before exhaust gases leave the facility. Some plants also use systems designed to capture carbon dioxide for storage or industrial use. Natural gas generally produces fewer carbon emissions than coal for the same amount of electricity, although gas plants still release greenhouse gases and must manage methane leakage throughout the fuel supply chain. After electricity is generated, it still cannot simply travel directly into household outlets. The generator typically produces electricity at a voltage that is much lower than the level required for efficient long-distance transmission. Large transformers located in the plant's switchyard increase the voltage dramatically. Higher voltage allows electricity to travel long distances with lower transmission losses. From the switchyard, high-voltage lines carry the electricity toward regional substations, where the voltage is gradually reduced before entering local distribution networks. The power grid must constantly balance electricity production and electricity consumption. Unlike many other products, electricity is difficult to store in enormous quantities using conventional systems, so generation must closely match demand. When millions of people turn on air conditioners during a hot afternoon, power plants must respond to the sudden increase. Grid operators coordinate multiple generating stations, transmission networks, battery systems, and other resources to maintain a stable supply. Modern power plants therefore do not simply produce electricity. They are active participants in a huge interconnected system that must remain balanced every second. Maintenance is another enormous operation. A power plant may contain thousands of pumps, valves, motors, turbines, transformers, sensors, and miles of piping. Engineers use vibration analysis, thermal imaging, oil testing, ultrasonic inspections, and other techniques to detect problems before they cause failures. Some equipment is monitored continuously, while major components such as turbine systems may be inspected during scheduled outages. Predictive maintenance software can analyze equipment data and identify patterns that indicate a component may need service before it breaks unexpectedly. As electricity demand continues to increase, power generation technology is also changing. Modern plants are becoming more automated, more efficient, and more flexible. Artificial intelligence can help predict equipment failures and optimize operating conditions. Digital twins can create virtual models of turbines, boilers, and entire power stations, allowing engineers to test changes before applying them to real equipment. Advanced turbines are being designed to extract more energy from the same amount of fuel, while new energy storage technologies can help balance supply and demand when electricity consumption changes rapidly. Although the machines inside a massive power plant can appear unbelievably complicated, the basic journey of energy is remarkably easy to understand. Fuel releases energy as heat. Heat creates a high-energy working fluid. That fluid drives a turbine, the turbine spins a generator, and the generator produces electricity. Transformers then raise the voltage so that the electricity can travel efficiently through the power grid and eventually reach homes, businesses, hospitals, factories, and transportation systems. What makes a massive power plant extraordinary is not one single machine, but the coordination of thousands of machines working together without interruption. Every pump, sensor, valve, turbine blade, transformer, pipeline, computer, and safety system has a specific role. Together, they transform the chemical energy stored in fuel into one of the most useful forms of energy in modern society. And every time millions of people switch on their lights, charge their devices, run their factories, or power their homes, somewhere inside a massive power station, an equally massive engineering system is working continuously to keep the electricity flowing.